Hello everyone, this is Yang Liu from the Beijing Institute of Control Engineering. So today I will give you a presentation about our work evaluating large language models for time series anomaly detection in aerospace software. I will introduce our work from the 6 parts. The first is background and motivation. Ensuring the safety and reliability of modern software systems is a critical concern. Time Series Anomaly Detection, or TSAD, is a vital technique for monitoring software system health by identifying abnormal behaviors in operational data. However, current approaches have key limitations. Supervised methods are limited by the scarcity of labeled anomalous data, while unsupervised methods struggle with generalization, leading to unaffordable maintenance costs. Large language models offer a promising training-free alternative due to their strong generalization capabilities. Figure 2 illustrates the pipeline. After preprocessing, we use two main paradigms. In the direct paradigm, the LLM acts as a classifier to find anomalies. In the prediction-based paradigm, it forecasts future data and anomalies are detected from the prediction error. Despite their promise, applying LLMs to aerospace software faces three challenges in practice. First is the complexity of aerospace data. The telemetry exhibits complex, intervariable relationships governed by feedback loops. As Figure 1 illustrates, this means anomalies can propagate through the system, potentially causing satellite damage, which makes detection very challenging for generic LLMs. Second is a misalignment of evaluation metrics. Standard point-based metrics like the F1 score do not reflect real-world operational practice, where users are concerned with actionable anomalies within a window of data, not just individual points. Finally is the lack of domain knowledge. Because they are trained on general-purpose data, LLMs lack the specific understanding of physical laws, sensor failure modes, and operational procedures necessary to interpret critical anomalies. In response to the challenges, our paper makes the following three contributions. First, we present the first systematic evaluation of LLMs for this task. To facilitate this, we introduce ATSAD bench, a comprehensive benchmark with 9 tasks covering diverse anomaly patterns and control loop scenarios, enabling rigorous comprehension. Comparison. Second, we propose three user-oriented window-level metrics: alarm accuracy, alarm latency, and alarm contiguity to assess the correctness, timeliness, and credibility of alarms from an operational perspective. And third, we investigate enhancement strategies like few-shot learning and RET and validate their effectiveness and limitations through both experiments and a real-world case study. Second, benchmark construction. Now let's look at how we constructed our benchmark, ATSAD bench. It is designed along two primary dimensions. The first is the three pattern-wise anomaly types, as defined on the slide and visualized on Figure 4. These include the fixed value anomaly and the deviation anomaly, which is further subdivided into const and time-varying types. These are all based on realistic on-orbit fault behaviors. The second dimension is the three control loop scenarios. These include univariate tasks for single-variate analysis and, more importantly, multivariate tasks. Within the multivariate setting, we make a critical distinction between in-loop scenarios, where faults propagate system-wide, and out-of-loop scenarios, where they remain isolated. Finally, the simulation and construction process was rigorous. The source for all our data was a high-fidelity aerospace simulation platform. Each experiment was designed to last 2,000 seconds, with a fault injected for the final 500 seconds. The resulting data was then subjected to critical pre-processing steps, including some inversion correction and removal of the initial stabilization phase to ensure high data quality. Third, study design. As mentioned before, standard point-level metrics often fail to capture the operational needs of aerospace system users. To address this, we aggregate model outputs at the window level. For each input window, we count the number of points flagged as anomalous. If this count exceeds a set threshold, the entire window is labeled as anomalous. Based on this foundation, we introduce three metrics aligned with industrial requirements. The first is alarm accuracy, which measures the correctness of these window-level decisions. The other two metrics are best understood visually using Figure 5. In this figure, each input window is visualized as a colored block. Blue indicates a normal input window. Pink denotes an abnormal window, where the detector fails to raise an alarm. And red signifies an abnormal window, where the detector successfully raises an alarm. Alarm latency, shown in Part A, quantifies timeliness. It measures the delay in number of windows from the true onset of an anomaly to the first successful alarm. Finally, alarm contiguity, shown in Part B, measures the trustworthiness and usability of the alarm system. In an operational scenario, dispersed alarms, as shown in the top example, are not actionable and can erode user trust. In contrast, contiguous alarms, shown in the bottom example, are reassuring and reliable. A signal an ongoing risk. Our ASE metric is designed to quantify this degree of alarm concentration. Now, I will detail the enhancement strategies we investigated. The first is few-shot learning. For the direct paradigm, the prompt included 1 positive and 3 negative examples with explanations. For the prediction-based paradigm, only the positive example was included to avoid biasing the model's predictions. The second strategy is REG. In this setting, reference windows were retrieved from the training set based on distance. The most similar window was then incorporated into the LLM prompt as additional context. Our study is designed around 4 research questions to evaluate the LLMs. First, we compare their performance against state-of-art unsupervised approaches using point-wise metrics on ATS-AD bench. Second, we assess if they meet practical operational requirements using our new window-level metrics. Third, we examine how much their performance can be improved through enhancement strategies. And finally, we validate their applicability on a real-world anomaly task. Fourth, results and analysis. In summary, here are our key findings for RQ1. First, LLMs perform notably well in univariate tasks, though they still lag behind state-of-the-art unsupervised approaches. Second, in multivariate tasks, they show a slight advantage in multivariate in-loop over multivariate out-of-loop. Third, the effectiveness of LLMs varies across anomaly types. Finally, among the two paradigms, LLMs achieve better results under the prediction-based paradigm. For RQ2, we found two main results. LLMs achieve higher alarm accuracy and alarm contiguity only in univariate tasks, whereas their performance in multivariate tasks is nearly equivalent to random guessing. The alarm latency does not follow this trend. The best result is an average of 1.22 windows. Moving to RQ3, we found that few-shot learning enhances the performance of LLMs under the direct paradigm, but exhibits limited capacity under the prediction-based paradigm. REG, on the other hand, does not demonstrate significant improvements across the tasks. Finally, for RQ4, we conducted a case study on a real-world anomaly. In the zero-shot setting, the Tianwen-3 finds the true anomaly but produces false alarms. Few-shot learning eliminates these false alarms, while REG leads to more. Fifth discussion. Our work offers meaningful insights for the practical deployment of LLM-based anomaly detection. However, we acknowledge several limitations. Our benchmark is based on simulation data. Our focus is exclusively on the aerospace domain, and the scope of the models and strategies we tested remains limited. Our work also highlights several important future directions. First, enhancing intervariable reasoning for multivariate data. Second, developing more practical domain-specific metrics. And finally, integrating domain knowledge through fundamental approaches like pre-training and fine-tuning. Finally, conclusion. To conclude, our work presents the first systematic evaluation of LLMs for TSAD in the aerospace domain, supported by our new benchmark, ATSAD bench, and 3 user-oriented metrics. We hope that our contributions will inspire further research and support the development of more effective approaches for this and other safety-critical domains. If you have any questions, feel free to contact me via email. I will respond promptly. Thanks for watching.